So you have two capacitors and they're connected in series. So that's the first capacitor. That's the second capacitor. And this one is 2 microfarads and this is 8 microfarads. And what's the total capacity? Well, be careful here. The formula is actually 1 over C equals 1 over 2 microfarads plus 1 over 8 microfarads. If I just get rid of the micro for the moment. So that means C equals so it ends up being C equals 8 over 5 microfarads.
So teacher,
yep.
we have it in we don't change it to microfarad?
I mean, I can put in 10 to the oh, sorry, that's not microfarad. Sorry, what's the unit? No, it is microfarads. Yeah. So, what were you asking me? Do I need the micro or not?
No. If the question given farad, not without micro.
Oh, it's fine. I mean, you could even get rid of the micro and put in 10 to the minus 6. It doesn't matter. It's okay.
So we don't need to change it, convert it to microfarad.
Oh, I understand. No, you don't need to. No. If the question was in farads, you don't need to give the answer in microfarads. Yeah. Determine the charge. So the formula for charge is Q equals CV. And you can't see it here, but there's actually a voltage. I'll put in a little voltmeter. There's 40 volts running across this. Okay. Well, that would be 2 times 10 to the minus 6 times 40. Which is 8 times 10 to the minus 5 coulombs. And then for the second one, it's 8. Oh, sorry, did I just do the... No, I didn't. No, it was fine. So now it's 8 times 40 times 10 to the 6. Now, determine the charge on each capacitor. Well, that's not technically, that's not really right. Because if you remember, when the capacitors are in series, the charge has to be the same. Otherwise, if the charge was greater in one of them, it would push electrons out from the other. So if the charge on the second one here was bigger than on the first one, then it would move until there's an equilibrium. Now, for me, I feel like I should say then the answer is going to be, well, you know what, I'm going to see what they do in the marking scheme, but I feel like I should just be taking the smaller answer of the two, which is the first one. So let me have just a quick check here. But I don't feel happy giving the two like this, but I'll see what they say. So we're looking for the one that starts off with 2 capacitors. No? That's the mark. Focus, Andy. You can help your teacher look at the screen. There we go. 2 capacitors. So it's number 5. Yeah. It looks like what they did, if you notice here, the C that they used was the C from the previous answer. So it should really maybe have said, what is the total charge in the capacitors? I guess would have been a little bit clearer. So rather than doing it like this, maybe this is just a little bit of English for you, maybe to help, and to help me too. So if it's in series and you want the charge on each, that amounts to the same thing as calculating it, the total charge. Now, if I was more awake, which I'm not, okay, I would have thought to myself, why did they ask me in part 1 to get the total capacity if I did not use it in part 2? Do you understand what I'm saying?
Yeah.
So here Q equals CV, which will equal 8 over 5 times 10 to the minus 6 times 40, which equals
6.4 times 10 minus 5.
which is what they had, wasn't it? Coulombs. Okay. Total energy, well, that's easy. The formula is a half C V squared. Wasn't that it for total energy? So a half times C times V squared. So I got 1.28 times 10 to the minus 3 joules. If the capacitors are combined across a large resistor, draw a graph to show how the current flows with time. So do you remember the graph for current? If I put time here and current here, what shape is this graph as the capacitor is discharging? Up or down?
Down.
Down.
From
Down.
1 to 3.
But is it charged already?
Yeah, it says, I take it as being charged because in the previous part they asked you to calculate the charge. Alright, so that's number 1 there. So the lesson we've learned is when it's in series and asking for the charge on each is the same as asking for the total charge, because if you remember the proof for the formula, I said if you have capacitors like this, that the charge on each here will actually be the same as the total charge, because the electrons push one out from the other. So it's like this one moves in here, pushes this out, this one moves in here, pushes this out. So out at the end is just like one of the Q's. So in other words, it looks a bit strange to say this, but the total charge is equal to the charge in each individual one. And you might think, well, why isn't it 3 times it if there's 3 of them? It's actually not. It's weird, it's weird, it's weird, I know. Alright, number 2 now.